There we go. Our next distinguished speaker is not here today, but you'll still hear from him anyway. My predecessor and mentor, David Petti, is joining us from Cambridge via audio, and will help with the visual part of this. Most of you know who he is and the role he's played. It's been said by at least one person on the inside that he saved the high temperature reactor industry. And I think there's some truth to that. He was one of the architects and executors of the AGR fuel qualification program. He led the R&D for the NGMP project and the ART project for many, many years before stepping down in that capacity, maybe 2 years ago, to take on other roles at the lab, and also as a prime mover behind the next upcoming edition of the MIT's report on the future of nuclear energy. And we're all looking forward to that. It'll be coming out later this year, be rolled out, and it has a lot of important things to say about nuclear energy and how it's going to be able to compete in the coming years. So, Dave, are you there?
Yeah. Can everybody hear me?
We can hear you just fine, thanks. And I'm here on the slide, so just let me know when.
Great. Okay. So, what I thought I'd talk about is a little retrospective on how we matured the key parts of HTGR, VHTR technology. And I describe it as a DOE success story. And I think as I go through it, you'll see why it was so successful. So next slide. This is my view of advanced reactors. In terms of what limits each system, I tend to think of light water reactors as thermal hydraulic machines, sodium fast reactors as physics machines, HTGRs as material machines, and salt systems as chemistry machines. So if HTGRs are material machines, then that should be where the focus is on the R&D side, and in fact that is the case on the next slide. When we started back 15 years ago, there were key needs in fuels, graphite, and high-temperature materials qualification. These had been around for easily decades from the old U.S. MHTGR program. When we started the R&D, the focus was to be on the needs of the technology. I joke that we were doing GAIN 10 years before GAIN existed. We worked very closely with the reactor vendors. We established at INL a technology development office for focus and integration with both the NGMP project and the vendors. We established NQA1 protocols, and we embedded our quality engineers into the R&D because we were concerned that some of the scientists and engineers had never really been involved in an NQA1 type research effort, and this was a way to provide some osmosis and to actually get the quality engineers very excited about what we were doing. And in fact, it's one of the success stories, I think, that we had. And third, we stayed away from politics. Frankly, the DOE programs, there are political boundary conditions and political forces all the time. We really tried to build some walls so that we could focus on getting what needed to get done. Looking back now, the fuel program is 15 years old. The graphite program is about 10 years old, and the high-temperature materials work was mostly completed about 3 years ago. There's some long-term creep testing that's going on that's just going to take a long time. But if you go back and you look at the original objectives and what we said we were going to do, it's what we did. They remain valid today. There's some minor changes, but by and large, 85 to 90% of what we said we needed to do, we did. And frankly, longevity in the DOE program is rare, and I tend to think that it was that success breeds success. On the next slide, I talk a little bit about the fuel program. And basically, there were 4 really high-level objectives. 1, make fuel as good as the Germans had done. This had never been done in the United States. There's a whole history of us not making really good fuel. Second, if we could make good fuel, we better irradiate it, and show that it'll perform to 1250 degrees Celsius and 19% FEMA. At the time, in 2003, this was a pretty bold performance envelope. Many were concerned that we would see failures at the high temperature and the high burnup when coupled together. So there was nervousness and risk. Third is if we could actually get some good fuel coming out of an irradiation, we might actually do something we'd never done, which is to put some fuel in furnaces at high temperature and see what they would do. We'd never had fuel good enough in the HTGR community in the U.S. to do this. The Germans had done a tremendous amount of this type of work, but we'd never done that. But we stood up furnaces, and we actually did it. And third was to take all this data that you get and improve and validate models on fuel performance and fission product transport. This sounds easy, because I could put it all in one slide, but it was a lot of hard work by the team, folks in Idaho, Oak Ridge, BWXT, and GA. The next slide just shows some of the accomplishments of the program. On the left is a plot of the fission gas release from a number of old irradiation capsules, the U.S. on the left, the Germans on the right, and then you can see the AGR1 in the blue X's and the AGR2 in the pink diamonds. AGR1 and AGR2 really changed the game, particularly AGR1, for what we thought about TRISO fuel in the United States. We had no failures going all the way up to 1250 degrees C for the irradiation and 19% burnup. AGR2, it's really hard to tell because we had some problems with the capsule itself. The answer is probably somewhere between 0 to 1. But when you take all that data and you translate it, we had failure rates that were 10 to 20 times better than what the designers required. And further, these irradiations were way more extreme than the reactor envelope as a whole. We were really looking at the upper end, if you will, of the reactor envelope. When we went to the safety testing, which is on the right, here we plot the cesium release from particles for hundreds of hours at either 16, 17, or 1800 in the different colors. We had really amazing performance, particularly at 1600 degrees C. Nothing failed after 300 hours. And the results were 5 to 8 times better than the designer requirements at the reactor level. Beyond this, I don't have a great slide because it would take me 5 slides to talk about it, is what we do in the post-irradiation examination. The PIE team, led by Paul Demkowitz and John Hunn and Bob Morris, really took the PIE to a new level. There's a tremendous amount of meticulous work. We have to demonstrate that the fission products stay inside the particles. So you've got to basically assay everything in the irradiation capsule to convince the NRC that that is, in fact, a true statement. A tremendous amount of effort to find the few failed particles that we had, to understand what drove the failure of one particle or 0 particles, to understand mechanisms, to understand where the fission products go. In fact, this whole area is now we're going to wrap in a bow and put in a topical report where we're going to title it, it's the performance demonstration of uranium oxycarbide TRISO fuel to the high burn-ups and high temperatures that we experienced. This really is the heart of the major accomplishment of the program, and so I'm excited that we'll get this topical report prepared over the summer. Next slide. The other thing we did is developed a fuel performance model called PARFUME, for particle fuel model. This actually started before this program. It started as an LDRD at INL, so we're talking like 2001. This just shows all the pieces and parts that are in the model, but the code is getting a little long in the tooth. The people who actually developed it are no longer with us, and so we had transitioned some of these models to Bison, and there's some more models that need to be transitioned to have the same complete capability as PARFUME. We're doing that soon. Next slide. Let me turn to graphite. The purpose of the graphite program was to characterize the radiation behavior and the creep behavior over the dose temperature window that you see. It consisted of 6 irradiation capsules AGC1 through 6, as well as extensive characterization of the material in the unirradiated state that you can compare to the irradiated state so you could understand any differential changes. And the biggest change here that's happened most recently is that AGC 5 and 6 are no longer happening. They're going to be replaced by high-dose graphite irradiations because these doses are fairly modest compared to the needs of the FHR, the HTGR communities, particularly the pebble bed, where you want to go to very high doses. So we're going to take samples from AGC 1, 2, 3, and 4 and put them in these other capsules called now HDG 1 and 2. Take those irradiated graphite specimens and irradiate them some more and go out to much higher doses where things should get very, very interesting. Next slide. In terms of the accomplishments in the program, we had analytical measurement labs in Idaho and Oak Ridge because there was lots and lots of measurements that had to be done on the thermophysical and thermomechanical properties. Thousands of samples were characterized in the unirradiated state, and then similarly, more like hundreds in the irradiated state. We had detailed characterization of graphite billets from all the major vendors. Today, AGC 1 and 2 are complete. AGC 3 PIE is complete. I'm sorry, it says AGR. I just can't get used to that. AGC 4 is currently in the reactor until next fall, and then the high-dose experiments will follow after that. Lots of data to make strong statistical inferences about variations in material performance and properties, lot to lot, and within a billet. So again, all really important for the licensing. The next slide shows just some of the data. We spent lots of money, so I got to show you just a little. The left-hand side are dimensional change, shrinkage of graphite for two major grades, IG110 and H451, compared to the historical data. And it's at least as good, if not in some cases a little better than the historical data. And in the lower right is the creep coefficient that you back out from these experiments, which I could talk a lot about because I think they're amazingly cool. But creep will determine the life of the graphite, and getting a better handle on what that creep coefficient is as a function of temperature is really important to establish the lifetime of the graphite and how long you can keep it in the reactor before you have to change it. The next slide talks a little bit about high-temperature materials. Back in the day, we did the material screening test to look at what candidate alloys we could use for the large metallic components. And here the focus was more on the VHTR, the higher outlet temperature material. There was already material that could be used for a 750 degrees C application. Then we established test loops to measure impurity impacts on the alloys and extended the models to predict that up to 1,000 degrees C. Along the way, we really worked with the vendors to say, hey, can we really use a light water reactor pressure vessel steel in the gas reactor application? We needed to get some more data to extend the code case. We did that. We took alloy 800H, another code case, and extended it. It's used in things like the core barrel, and extended that code case to 850. And then a lot of the effort was developing data to codify Inconel 617 for use in the VHTR, and that draft code case was submitted to ASME. So that's just sort of a highlights of all the major accomplishments that the program has had over the last 10 to 15 years. And that's all I have to say.
That's good, Dave. Thank you. Any questions or comments to Dave before he signs off? Okay. Thank you, Dave.
Okay.
Never mind. Hang on.
Bye-bye.
Which reactor is handling most of the graphite irradiations? Where is that being conducted at?
ATR, out on the desert. Okay. Now you can go. Go back to work.